Welcome. Today, we're going to break down the fundamental rules that make electricity, well, move through a circuit. We're going to demystify voltage, current, and resistance and see how they all work together in a really logical system. Okay, so let's just dive right in with the most basic question you could ask. We talk about electric current all the time, but what's the actual force? What's the push that gets all those charges moving in the first place? What's the engine behind the flow? So, here's how we're going to tackle this. First, we'll define that electrical push. Then we'll figure out how we measure it and uncover a super simple but powerful rule that connects everything. After that, we'll look at the hurdles that try to slow things down, before finally putting it all together to see how this works out in the real world. All right, let's get into the core concept that makes charge move, and that's something we call electric potential. The key idea here, and it's a big one in physics, is that things love to move from a state of high energy down to a state of low energy. The best way to picture this is with a super simple analogy. Just like a ball will always roll downhill from a high spot to a low spot, electric charge does the exact same thing. It naturally moves from a point of high potential energy to one of low potential energy. It's that difference, that electrical slope, that creates the push. Now, this is actually a really interesting distinction. On one hand, you have electric potential, which is kind of this big theoretical idea about bringing a charge in from infinity. But in the real world, what we actually care about is potential difference. That's the practical, measurable push between two specific points right here in our circuit. That's the one that really matters for our devices. So, we've got this idea of an electrical push. But how do we actually measure it? When we have a standard unit, right? And that unit is the volt. And the relationship here is just beautifully simple. Potential difference, which we use a V for voltage, is just the amount of work done, that's W, divided by the amount of charge that got moved, which is Q. It's basically a measure of energy per chunk of charge. And here's the crucial point. We officially define 1 volt as the amount of electrical push we have when it takes exactly 1 joule of energy to move 1 coulomb of charge between 2 points. It's just a clean, direct, one-to-one definition. And to measure this in a real circuit, we don't just guess. We use a special tool called a voltmeter. You connect it to 2 different points, and bam, it tells you the potential difference, the voltage right between them. Okay, so now we get the push. That's voltage. So let's look at this fundamental rule that connects the push to the actual flow of electricity, which we call current. And this is where the famous Ohm's law comes into play. This right here is Ohm's law, and it's probably one of the most important relationships in all of electronics. It describes this wonderfully simple and direct connection. Basically, the more push you apply, the more flow you're going to get. And this shows you exactly what directly proportional means in the real world. You crank up the voltage, the push, and the current. The flow goes up right along with it. You turn the voltage down, and the current goes down too. It's a super predictable one-to-one thing. But wait a second. What stops the current from just flowing like crazy? If we keep turning up the voltage, why doesn't the current just shoot up to infinity? Well, that's where our next critical piece of the puzzle comes in: resistance. And hey, we've got another great analogy here. Resistance is exactly what it sounds like: an obstruction. Think about trying to run across a path that's just covered in stones. It's going to be harder, right? That's what resistance does to electric current. It's basically the electrical version of friction. So what decides how much of this electrical friction a wire or a component has? It's not just random. It actually depends on 4 main physical things. First up, length. And this one is pretty intuitive, right? The longer the wire, the more road the electrons have to travel, and the more little obstacles they're going to bump into. So longer wire equals more resistance. Next up is the cross-sectional area, or just how thick the wire is. Think of it like a highway. A really thick wire is like a 5-lane freeway. Tons of space for traffic to flow easily. That means less resistance. A thin wire? That's like a tiny country road, creating a bottleneck and a whole lot more resistance. And here's why this stuff actually matters in the real world. Temperature has a huge effect. When something like an electric motor gets hot from being used, the resistance inside its wires actually goes up. This makes it harder for the current to flow, and the motor starts to work less efficiently. And finally, the material itself is absolutely critical. Different materials are just naturally better or worse at letting electricity flow. So while silver is technically the absolute best conductor with the lowest resistance, it's way too expensive for everyday stuff. And that's why copper is king for the wiring in our homes. It's this amazing balance of really low resistance and being affordable. Okay, let's bring all this home. We're going to see how these concepts aren't just theory in a textbook, but are actually the tools we use to analyze and solve real problems. So let's use that formula we learned. Remember V equals W over Q? We can just rearrange that a little bit to find the work. So work equals V times Q. We've got a potential difference of 6 volts and a charge of 1 coulomb. We just multiply them together. 6 times 1 is 6. So the answer is 6 joules of energy. See? Simple as that. So at the end of the day, understanding this relationship between voltage, current, and resistance, it gives you the power to predict and control electricity. These aren't just abstract rules, they're the actual tools for innovation. So I'll leave you with this final thought. Now that you know these fundamental principles, what choices would you make to design a better, safer, or more efficient circuit for the future?